And now we'll move into indoor air quality and mechanical ventilation.
The 2019 standards include requirements for mandatory mechanical ventilation and for HERS verification of the installed performance of those ventilation systems. California adopted ASHRAE 62.2-2016 as the standard, with one exception. Although it is permitted by ASHRAE, California explicitly prohibits opening and closing windows as an acceptable option for providing whole house ventilation. California requires a mechanical ventilation system, both for the entire house as well as specific locations such as the kitchen and bathrooms and laundry rooms. Now, in this section, we're going to cover the Title 24 requirements. These are targeted more at what the builder has to do to comply. We're not going to cover the test procedures and all of that. For the HERS verification, we'll be covering those in the mechanical ventilation section, how to test them and what all those processes are for you. So this one we're going to cover just those requirements, how much ventilation is required, how we calculate those, and any additional requirements that the builder has to comply with. There are additional general requirements that aren't necessarily directly related to the mechanical ventilation system, but they overall they contribute to the indoor air quality of the home, which is what we're trying to improve with these mechanical ventilation systems. So we need to make sure that the wall and any openings between the house and the garage are sealed. Now, if we remember back in the insulation section, that's already required. You have to seal all these openings, and that's to stop the movement of air. That's more for the energy efficiency side of things, but it is twofold in that it also will help to improve the indoor air quality of the home. If you do install a supply mechanical system, this is where it's going to bring air from the outside to the interior of the home. You do need to install filters that are rated at a MERV 13 or better. So MERV is just the standard rating, the efficiency rating, and so 13 is a pretty efficient filter, much better than what they used to be. And then we also need to install a CO alarm in each dwelling unit, and that has to be done in accordance with the regulations outlined in NFPA 720.
It's required in all new buildings and any additions to existing buildings over 1,000 square feet. Kitchen and bathroom shall be mechanically ventilated to the outdoors. Clothes dryers shall be vented to the outdoors. And keep in mind that for multifamily units, dryer can be vented to the outside together as long as there is a damper present to prevent recirculation of exhaust air from one apartment to the other, meaning that they don't necessarily have to have their own individual vent to the outside as long as that damper is present. And then also combustion appliances shall be properly venting and air systems shall be designed to prevent backdrafting. In the second bullet where it says kitchen and bathroom shall be mechanically ventilated to the outdoors, one thing I want to point out is when we say outdoors, we're talking about specifically to the overall outside of the building envelopes. So basically, if they're ventilating just to an attic or to a crawl space or to other some type of soffit, that is not allowed. They have to go to the outside of the overall structure. In addition to that, when we're talking about kitchens, kitchens have to be vented to the outdoors as well, meaning that if there is a self-recirculating hood in the kitchen, those are not sufficient. In addition to that, there has to be an actual ventilation system that vents the kitchen again to the outside. So there's different type of mechanical ventilation. And one thing I was going to point out is please do not confuse the indoor air quality and mechanical ventilation requirement with the whole house fan requirement, which is a space cooling requirement, which we'll talk about later in the HVAC section. These are two completely separate requirements. Indoor air quality and mechanical ventilation has to do obviously with the quality of the air that we're breathing inside the house. The whole house fan requirement has to do with space cooling. So two totally separate applications and requirements. So back to this, whole house mechanical ventilation types. There's different types that we can see. The most common type that you'll see in home is going to be the exhaust ventilation. So this is an example of a bathroom fan, laundry room fan, or it could be just a fan located anywhere in the house, basically exhausting air from the house. It's usually the most common solution. There's pros and cons, obviously. The pros are they're easy to install. It's a specific source control of pollutants, so it can be located in a specific area, right? The cons is the fact that the makeup air comes from uncontrolled sources. So as the air is being exhausted out, it's got to pull air from somewhere else, right? Because for, like we talked about in the building science section, for every CFM that goes out, one CFM must come in. So for some reason, that air is coming in from somewhere, but we're not controlling where the air is coming from. One or more fans can meet the requirement, and it can be a dedicated whole house system, or it can be for both local and whole house use. Now for supply ventilation, there's different things that we can see out there. So in this particular scenario, it's the supply ventilation with a dedicated fan. So this is very similar to the exhaust ventilation, except that now the fan is supplying air into the house and not expelling it outside of the house. But it's the same principle of installation. Like I said, it works opposite of exhaust ventilation. The pros are that it controls the source and delivery of makeup air, and the supply must be filtered. So basically, because anytime you're bringing air in from the outside, you have to filter that air. So the filters clean the air as it's pushing through. The cons is the fact that there is no source control exhaust of pollutants and can drive moisture into the building shell. Obviously, if there is moisture outside, if it's pulling it into the house, that's going to be an issue, or it could create issues. The outdoor air inlet must be placed to avoid known areas of contaminants, and if a dedicated fan is used, care must be taken to avoid introducing too much outdoor air into one location. Now, the other option, or the other example of supply ventilation, it's a central fan integrated supply ventilator. So this is a fresh air vent that's introduced into the HVAC system, and it's using the blower from the HVAC to basically pump the ventilation air through the supply ducts of the HVAC system. A CFI system can be configured to function through the central air system, or the FAU. The pros is that it's a simple design. The outside air is mixed and distributed evenly throughout the house. The cons is the fact that it uses a very large central fan to bring a small amount of air, which basically you're using a lot of energy to bring in little amount of air. So it's going to raise your energy bill a little bit. It does pressurize the home, and it can impact the duct leakage test because you're adding a vent to the outside to the HVAC system. That should be dampened, but it could create leakage in the ducts when the ducts are being tested or down the line. It must have an automatic damper installed that cannot be taped during duct leakage testing, like I mentioned. And then when a CFI system is used, the field verification for fan watt draw is triggered for the ventilation system. So if the fan watt draw test was not required before, with this system, it will be. In addition to that, one thing that I wanted to point out was the fact that if you have a home that has a CFI system installed in relation to sampling, and the HERS rater is testing that particular house, that house cannot be sampled with homes that do not have a CFI system installed in it. It has to be kept separate. And the last example that we have is a combination or balanced ventilation. So this could be an example of a heat recovery ventilator, energy recovery ventilator, HRT, HRV, ERV. So basically, it's a neutral pressure in the house. You basically have a system that's bringing in air in and exhausting it at the same time, exchanging it through. So you basically have neutral pressure in the house. Now, these can be very expensive. It could also be applicable by having an individual supply fan and an exhaust fan that supply and exhaust an equal amount of air. So that would be the cheaper way to achieve this particular type of ventilation. And like I said, it uses both exhaust and supply fans, supplying the same airflow and creating neutral pressure in the house. The pros is the fact that it has source control pollutants, and it has an opportunity for heat recovery ventilator, even though it's much more expensive. And the cons, obviously, is the cost and the complexity of the system. Now, heat recovery ventilators provide balanced ventilation while recapturing heat from the exhaust air to temper the incoming supply air. So there are some energy savings with a HRV or an ERV, but the initial cost of those systems are much higher than everything else we talked about so far. Now, as far as the whole house ventilation, it may operate continuously or intermittently. The whole house ventilation rate is determined for continuous ventilation, and if the system is operated intermittently, an adjustment is made. Whole house mechanical ventilation rates, that's both continuous and intermittent, have to be verified by a HERS rater. And we're going to talk about the procedures to verify those items down the line. So it's not going to be explained in this particular section.
So these ventilation rates are determined by using the formula below. And this formula is for a continuously operating system. If you are going to install a intermittent system, then these values are going to increase, and that's going to be determined based on the amount of time that the system runs versus the time that the system is off. And we'll cover that calculation later. So the ventilation rate is calculated by the calculation here. So we have 0.03 times the conditioned floor area, and then we add that to the result of 7.5 times the number of occupants. Now, number of occupants is going to be the number of bedrooms plus 1. So if it's a 3-bedroom house, the number of occupants is going to be 4. Now, when you're using a combination ventilation system, so it's the balance system where you have both supply and exhaust at the same time, the installed ventilation rate is going to be either the larger of the supply or the exhaust. You don't get to add them together. So if you have 50 CFM of supply and 50 CFM of exhaust, that doesn't equate to 100 CFM of ventilation. It's going to equate to 50 CFM because that's all the air that's being moved. So now let's look at an example of how we would calculate that. So let's say that we have a 4-bedroom, 2,000 square foot house. We're going to calculate for continuous ventilation. And so we've got our equation here. It's going to be 0.03 times 2,000 because that's the square footage of the house, the conditioned floor area. And then we're going to add that to the result of 7.5 times 4 plus 1, which again, 4-bedroom house plus 1, so it would be 5 bedrooms. So if we get the result of the first part of that equation, that's going to be 60. The second part of the equation is 37.5. We're going to add those together, and we're going to get a total of 97.5 CFM. So that's what we need to size the system to run. A continuously operating fan that can provide 97.5, a minimum of 97.5. Oftentimes, those fans are going to be rated in more even values, so it'd most likely be a 100 CFM fan. So you need to make sure that that is installed and that the piping system, the ductwork for that is able to also achieve that value.
Now, intermittent ventilation is the other option that we have. So continuous means that it runs 24/7. Intermittent, it means that it comes on and off at preset times. So intermittent ventilation is permitted as long as the ventilation airflow is increased to respond to the fewer hours of fan operation. So basically, because the ventilation is coming on and off, the lower the amount of time that it's going to be on, the more CFMs the ventilation will have to bring in to make up for the times when it's not running. So the increased flow, again, depends on the fraction of time the fans operate. Less time the fans operate, the greater the intermittent airflow will have to be. Intermittent ventilation systems have to be automatically controlled by a timer or other device that assures that they will operate the minimum amount of time needed to meet the ventilation requirement. So the system will come on and off automatically. The homeowner is not going to be turning the system on and off when they remember to do it. This is an autonomous system. So as far as the controls for whole house mechanical ventilation, they must have an override control readily accessible to the occupant. The occupant must be able to modify the settings and override the system. It must be clearly labeled as the mechanical ventilation control, and then instructions on how to use the system must be provided to the homeowner. So even though we said the system must be autonomous and the homeowner cannot mess with it, at the end of the day, there still needs to be a control of some type accessible to the homeowner that he or she can use for emergency reasons or maintenance purposes. And that switch, again, has to be readily accessible. So it cannot be buried in an attic somewhere. It cannot be under a floorboard or something, whatever it may be. It has to be readily accessible. And by readily accessible, it means that it has to be within reach of the homeowner without outside assistance, meaning they don't have to climb on a ladder, they don't have to dig a hole, they don't have to do anything crazy to get to that switch. And then, like I said, it has to be clearly labeled as the mechanical ventilation control. Now, the only switch that has to be labeled is the switch for the whole house control. So any kind of mechanical ventilation system in the house that is not whole house mechanical ventilation does not have to be labeled. It's only the whole house control that has to have that label.
Now let's take a look at local mechanical ventilation. So local exhaust, which is sometimes called spot ventilation, has long been required for bathrooms and kitchens to remove moisture and odors at the source. Building codes have required an operable window or an exhaust fan in bathrooms for many years and have generally required kitchen exhaust either directly through a fan or indirectly through a recirculating range hood and an operable window. The energy standards recognize the limitations of these indirect methods of reducing moisture and odors and requires that these spaces be mechanically exhausted directly to the outdoors even if windows are present. Moisture condensation on indoor surfaces are a leading cause of mold and mildew in buildings. The occurrence of asthma is also associated with high interior relative humidity. Therefore, it is important to exhaust the excess moisture from bathing and cooking directly at the source. Now let's look at local mechanical ventilation rates. So we have whole house mechanical ventilation and we have local mechanical ventilation. Whole house is one or more fans that provides ventilation for the entire home. Local ventilation fans are going to provide that for a very specific location, such as kitchens and bathrooms and laundry rooms. So if we look at the different required rates, we have it broken down in both intermittent and continuous. So on the intermittent side, if we have an enclosed kitchen and it's a vented range hood, it needs to provide 100 CFM. If it's a different type of exhaust fan, it needs to provide 300 CFM or 5 air changes per hour. If it's a non-enclosed kitchen, again, vented range hood is 100 CFM and any other type of exhaust fan is going to be 300 CFM. And then bathrooms are going to be a set rate of 50 CFM for intermittent ventilation. Now, intermittent on these is essentially going to be more of an on-demand. This is what you're going to be used to. Is there's going to be a switch, and when you need to use it, after a shower or while cooking, you're going to turn that fan on. It's going to run while it's needed, and then you're going to turn it off when you leave the room. Now, you do have the option to run a continuous fan. And for kitchens, it would need to provide 5 air changes per hour, and bathrooms would be 20 CFM.
Now for controls, for local ventilation, the only requirement is that there must be a control. It could be manual, like a regular wall switch. It could be automatic, where you have occupancy sensors and delay off switches. But as long as there is some type of control, it's good to go.
Now the whole house and local ventilation does have to meet certain sound requirements, sound limits. The guidelines for that is going to be for any continuously operating fans, whether it is a whole house fan or a local fan, can be 1 zone or less. And now these ratings, these zone ratings, are the manufacturer's listed rating. Manufacturers are required to test for sound on all their equipment, and they will put that on their labels. If it's an intermittent whole house fan, no more than 1 zone. If it's an intermittent local fan, where it's not doing any whole house ventilation, it's just for that local fan, it can be up to 3 zones if it is less than 400 CFM. If it's more than 400 CFM, there is no sound requirement, and you're not usually going to see those except for on some large range hoods. The very large ones can move more than 400 CFM. So range hoods are an intermittent local fan, and they must also be rated at 3 zones or less. But this sound rating is going to be at the working speed of 100 CFM. So if it has multiple levels, a lot of them will have 2, 3 speeds. If the low speed is 100 CFM, then that is considered the working speed, and that's where it must be 3 zones or less. Speeds 2 and 3 are 250 and 400. It's not going to have to meet those zone requirements, only at the 100 CFM.
Now, as far as the sound rating is concerned, though, inline fans do not need to meet the zone requirement if there is at least 4 feet of duct between the fan and the intake grill. So an inline fan, if you've never seen that, is basically a mechanical ventilation fan that's used for exhaust for the most part, where the fan itself is not located right where the grill is. So basically the fan is located at a remote location, and then there is a duct that goes from the fan all the way to the grill that you see inside the house. So that's an inline fan. So as long as there is at least 4 feet of duct between the fan and the intake grill, that particular inline fan does not need to meet zone requirements. So let us know if you have any questions via the messaging system, or shoot us an email or give us a call. There was definitely a lot of information covered in this PowerPoint, and this is new material to you. I would be surprised if there was no questions. So feel free to reach out to us, or save your questions for the field training, so you'll be able to ask the questions to your field trainer.